So now I'm going to talk about Hooke's law. This is about springs now. Hooke's law says that the force required to maintain an ideal spring, stretched or compressed x units beyond its natural length, is directly proportional to x. So basically, F sub x equals some number k times x. This is a non-constant force because F changes with displacement. So, for example, if the spring is at its natural length, the displacement from its natural length is 0. So it takes 0 newtons of force to maintain that spring at its natural length, right? You don't have to do anything. But if the displacement is x1, like right here, then it's going to take k x1 newtons to maintain that spring at that displacement, right? So that's how much force you have to apply on the spring to keep it at that length. All right, so F sub x is the force required to hold the spring at a given displacement. K is the spring constant. The spring constant is a measure of the stiffness of the spring. So the larger K is, the stiffer the spring. And also, the larger K is, the stronger the spring's pull or push is for a given displacement.
If you buy some springs at like I don't know Home Depot or somewhere wherever they sell springs, it'll probably tell you the spring constant.
I never looked at the number, but yeah. They can vary a lot. Like if you're using like those toy like slinkies, then the spring constant's going to be pretty low. It's not very stiff. So maybe like 1 newton per meter. But if you're talking about the stiffer springs, like for your car's suspension, then K could be like 100,000 newtons per meter. Anyway, x is the displacement from equilibrium. So equilibrium means that the spring is at its natural length, so it's not stretched or compressed. Basically, the net force is 0. The question is now, what is the work done on a Hooke's law spring by an external force to stretch it from x1 to x2?
Well, it's a variable force.
Yes, the force varies. It's directly proportional to x. So we have to do an integral. It's an easy integral though. So work, remember from the first page, is the integral from x1 to x2 of f sub x dx. So f sub x for a Hooke's law spring is kx. And what's the integral of kx with respect to x?
1/2 x squared times k.
Exactly, 1/2 kx squared. So you get that w is 1/2 k x2 squared minus 1/2 k x1 squared. So that's the work done by an external force to stretch the spring from x1 to x2. And even though in the diagram we have x2 is greater than x1, which is greater than 0, you can have x1 and x2 be negative, or you can have x1 negative, x2 positive. So it doesn't have to be exactly like this diagram. It works for compression of a spring as well. So that's Hooke's law. This is for an ideal spring. So not every spring is going to have the force required to maintain it be directly proportional to x. Maybe for a non-ideal spring, you can have like F equals kx squared, something like that. But this is the simplest case, and that's what a lot of physics classes talk about. One tiny detail that's not really a big deal is Hooke's law holds provided that x is not super large, but we're not really going to see that.
So if x is 1 light year, this doesn't hold.
Yeah, yeah. If you stretch the spring like some crazy amount and you ruin the spring, then yeah, Hooke's law is gonna fall apart. Let me just actually label one tiny thing as this is at equilibrium. This is the natural length. All right, so let's do an example with this. Suppose that 2.5 joules of work is needed to stretch a spring from its natural length of 25 centimeters to a length of 35 centimeters. How much work is needed to stretch the spring from 30 centimeters to 34 centimeters? Let's look at the first sentence. So I'm assuming this is a Hooke's law ideal spring. Let's call this 2.5 joules. Let's call that W1. And we know that the work done by an external force to stretch a spring from x1 to x2 is, we just derived that, it's 1 half k x2 squared minus 1 half k x1 squared. In this case, in this first sentence, what's x1 and what's x2?
X1 would be 0 and X2 would be 10.
Very good. So remember, x is the displacement from equilibrium, displacement from its natural length. So its natural length is 25 centimeters. So x1, that's where it's starting off, is it starts off at its natural length. So x1 is 0 centimeters. And then at 35 centimeters, it's stretched 10 centimeters. So x2 is 10 centimeters.
They like to trick you at that.
Yes, very important. We have W1, we have X2, we have X1, but we don't have K, unfortunately. So let's look at this second sentence now. We're trying to figure out how much work is needed to stretch the spring from 30 centimeters to 34 centimeters. So let's call this work W2, and we don't know what that equals right now. So W2, same idea. Instead of x1 and x2, I'm going to use x3, x4. So 1 half k x4 squared minus 1 half k x3 squared. So x3, 30 centimeters is 5 centimeters displacement from its natural length. So right here, this is x3 is 5 centimeters. And 34 centimeters, that's 9 centimeters more than 25. So x4 is 9 centimeters. So in this equation, we know everything but k. So we only have one unknown. So we can find k. And then we can plug in k here, and we know x4, x3, and we can find W2. What I'm going to do to find k is let's factor out 1 half k. And you're going to be left with x2 squared minus x1 squared. And x1 is actually 0, so let's just cancel that out. And to find k, I'm going to multiply both sides by 2 and divide by x2 squared. I'm going to plug stuff in because k is a number you use a lot for these problems. So I don't want to like leave it in variables because I'm going to eventually need that number later. So W1, that's the 2.5 joules. And x2 is 10 centimeters, but we need it in meters. So all the units work out. So that's 0.1 meters. And we're squaring it. So let's just take a look at the units quickly. We have joules in the numerator, meters squared in the denominator. Joules is newtons times meters over meters squared. So one of the meters cancel and you get Newton over meters. If you put this in your calculator, or you can even do it without a calculator, you'll get K is 500 Newton over meters. So we have K. We can use that K here, and we know x3, x4, so we can find W2. I'm just going to factor out the 1 half K. So we have 1 half K, which we just figured out is 500 Newtons per meter. X4 is 9 centimeters, so 0.09 meters, and we're squaring it, minus x3 squared, so 5 centimeters, which is 0.05 meters, and we're
Yeah.
squaring.
I would recommend converting centimeters to meters, everything to the right base units right off the bat, because you might forget it later.
That's true. So if you put this in your calculator, you'll get W2 is 1.40 joules. That's the work needed to stretch the spring from 30 centimeters to 34 centimeters. All right. Part B. How far beyond its natural length will a force of 65.5 newtons keep the spring stretched. How far beyond its natural length? That's displacement. That's x. This is F sub x. So what relates the two?
Hooke's law.
Yeah, we know F sub x is kx. So we're trying to find how far beyond its natural length. So we need to find x. So you just have to divide both sides by k. So F sub x is 65.5 newtons. And then k, we know from part A, is 500 newtons per meter.
It is satisfying to watch the units check out.
Yeah, so the newtons cancel, and then we have 1 divided by 1 over meters, so it just becomes meters. So that's exactly what displacement is measured in. So if you put this in your calculator, you get 0.131 meters. You could also say 13.1 centimeters since the problem's in centimeters. Okay, last part, part C. 0.5 kilogram block is attached to the same spring on a frictionless horizontal surface. The spring is stretched to 42 centimeters from its natural length and then released from rest. Find the block speed when the spring length is 35 centimeters. We're trying to find speed. So, what equation has speed in it?
The work energy theorem.
Yes. So we're gonna have to use that. So we know the total work is 1/2 mv2 squared minus 1/2 mv1 squared. So it says that it's released from rest. So that means the v1 is 0. So we can just cancel that out.
Love it when that happens.
So we're trying to find v2, the final speed, and we know m, so we just need to figure out what the total work is. The only thing that's doing work is the spring on the block. So there's no friction, and the weight and the normal force are perpendicular to the displacement. So only the force of the spring is doing work. That means we can use this for work total. But this is an external force acting on the spring that stretches it. But what we're dealing with in this problem is the spring is doing work on a block.
Devil's in the details.
Yeah. So it's the negative of 1/2 kx2 squared minus 1/2 kx1 squared. So this equals 1/2 mv2 squared. Very important here, this negative, because again, the spring is doing work on the block. It's not us applying a force to the spring and us doing work on it. So let's figure out what x1 and x2 are. So x1, it's stretched to 42 centimeters. The natural length, remember, is 25 centimeters. So if you subtract the two, you'll get that the displacement is 17 centimeters, which is 0.170 meters. That's x1. X2, we're looking at the displacement from 35 centimeters. So if you do 35 centimeters minus, the natural length of 25 centimeters, you get 10 centimeters, which is 0.100 meters. All right, so we know pretty much everything. X1, X2, we know K, we know M. We can find V2 now. So let me algebraically find V2 and plug everything in. So let me factor out the 1/2 K and distribute that negative. Because of the negative, everything switches. So it's X1 squared minus X2 squared. And this equals 1/2 mv2 squared. And 1/2s will cancel out. And to find v2, I'm going to divide by m and take the square root. So we can plug everything in now. So if you put this in your calculator, you'll get v2 is about 4.35 meters per second. That is it for today. Don't forget to like and subscribe, and I'll see you guys in the next video.
I